Oh.
Oh, you spread yourself out well. Good job. Usually they just group up. Anyway, if you'd like to chat with any of these nice people, they just raised their hand. Anyway, it's a pleasure to introduce Chris Fregly. Did I just get that wrong?
Yeah, so Fregly. Yeah,
Fregly. Who's coming to us from IBM and previously from Databricks, and is talking about probably one of the more exciting topics and developments right now in Spark. And so I'm just going to hand it directly over to Chris. And we do have a hard stop here at 2 o'clock, traditionally end at around 1:30. Questions may or may not make this longer or shorter. And as usual, you can come swarm the person afterwards if you'd like. He's agreed to this. All right, so let's welcome our speaker.
Thanks, guys. Thanks for having me. I first came to this seminar series. Yeah, it was probably one of the early. Yeah, was it like 2 years ago, maybe, like a year and a half ago? It was pretty close to Databricks, so because we're right on Beal and Scott or Beal and something over there. So I would just come over at lunch, and it was really, really good. There was one speaker I remember. He didn't have any slides, and that freaked me out. Yeah, do you remember that guy? And he just talked, and it was like the best talk ever. And I'm like, I cannot do that. I need like slides and props and all kinds of stuff. So. Who here is using Spark right now in your projects or your, okay, wow. So you guys are going to have a lot of questions. Have to leave time for that. I think we have a hard stop at 2. This talk, I was telling David, could be 3 hours or could be 30 minutes. So would you guys rather see demos and then look at the slides later? I'll post them. Yeah, who wants that route? Like, do you want demos, do you want code, or do you want slides and concepts, and then you can... Yeah, I mean, both are available. All right, so I'll do like a mix here, I think, which is famous last words for this is going to be a disaster. But let me make sure my demos are going. All right, that's not good. One sec here. Attached to it. Uh-oh. Okay, let me get this working. So I've got everything, all the demos that you'll see today in code are all available on GitHub. They're in a Docker image, and you guys can pull them down and actually run them live on your own machines. Let's see, let me attach here. Somehow it got disconnected after I switched over. Bin. Okay, so while that's building, let's get to the slides, do some intros. Okay. Oh, one disaster after another, huh? Okay, so I'll just start talking. My name is Chris Fregly. Previously Netflix. You guys already saw that slide. That's my mom. First day I moved from Chicago to California. My mom had to come with me like it was a school bus, situation. First day at school. So I got a picture of her. We took her for sushi, and she didn't know how to eat sushi. We realized, and she didn't trust the fish at the sushi place, and the usual mom stuff. So she got the avocado. It was pretty funny. I started dabbling. So actually at Netflix, we basically started building Spark streaming, right? So this is before Spark. It was kind of around the time of Kafka. The whole use case was to be able to actually tap into a live stream as. So yes, I was on the streaming team, which is not the actual video streaming, but all the play events when you press play and what starts the streams. So those statistics about how Netflix is like 1/3 of all internet traffic, that's true, but it's actually not coming from Netflix servers. It's physically coming from the actual, like CDNs, like Limelight or like Akamai and that kind of stuff. So so the streaming team was actually collecting these events, or like play events, stop events, just trying to figure out where people were, or like bailing out of a video, that kind of stuff. So the goal was to be able to tap into that stream live, which we didn't have that ability. Hey, Sonia. So yeah, we started building it. Kafka wasn't like really, first-class citizen back then, so we didn't work with it too much. So yeah, worked on that a little bit. And then, started studying Spark. So kind of got involved in Spark about 0.7, 0.8, and it was super intriguing to me about the machine learning and the graph processing and all that kind of stuff, right? It was super cool stuff. And then, of course, streaming. Yes, I had this meetup also. Let me show you this. Yeah, we hit top 3 the other day after the Martin Odersky. Thursday we had Martin Odersky in town. He somehow decided to come to my meetup, which was cool. We have 2,400 members, 2,500 Docker downloads. So the Docker stuff that you guys will see today, 2,500 people have downloaded that. They've been playing with it, starting to really contribute back to the GitHub repo. So I started this meetup to sort of dive deep and like surface patterns, right? So I want to bring out things that you wouldn't be able to see just sort of going through examples and that kind of stuff. So spend a lot of time on that. Spend a lot of time, obviously, scale, distributed systems, that kind of thing. Oh yeah, so someone got me a cake for the 2,000 member mark the other day. Yeah, that was kind of cool. All right, so let's start with the demo, assuming this thing started up. All right, that's still loading. Okay, so we'll cruise past that and get back to it. This is what the demo is going to be, once it comes up. So we'll be users in like the upper left. You'll be presented with about 80 technologies, and you can sort of click which ones that you currently use in production. Each time that you click, that goes to Kafka, right, like using the REST API. And then Spark Streaming is going to be listening on that Kafka stream and then pulling things down, storing them in Cassandra. It's going to be storing aggregations, it's going to be doing approximations. It's going to be building machine learning models like collaborative filtering, that kind of stuff. And then we'll come down and be, like Miss Data Scientist person over there, and we'll actually start analyzing with things like IPython and Zeppelin. So we'll see these tools sort of in action. We'll build the models, then push them out, and then you can actually see the recommendations. So let's see if this. All right, there we go. So here is, we'll start the Spark streaming. So this is the Cassandra side of things. So let's see here. .36060. So again, this is all running within Docker. I was forced to switch over to the IBM software instance when I joined IBM. I was Amazon for 6 years before that, but it's crazy, right? Like when you go from, from like an EC2 sort of just a normal, networking situation to a bare metal software instance, it's like night and day. You can it's crazy fast. That's my only IBM pitch there. So, all right, let's see. Why did that not complete? Okay, something's up here. All right, so let's just get back to the presentation. Okay, so we'll start off with scaling with parallelism, and then the ability to compose things, right? That's sort of the holy grail, where you can distribute things out, right? Do operations, do additions, do mins, do maxes, and then pull it down and aggregate. Come on. All right, so there's kind of a little sketch. Say that you want to add up all those numbers. It's pretty basic stuff, right? You could either do it the slow way, which is just do them all sequentially, right? So single thread going through, adding them up, or you can spread them out, distribute them out. So you go from O(n) to O log n. So these are composable operations, right? These are the associative, so you can do max, you can do set unions, yeah, you can do addition, multiply. Yeah, so division, yeah, division's not good, right? This is not something that we could split up very easily. So of course division was right, like invented by the Egyptians, probably what, 10 years ago, 20 years ago, I think. So yeah, what were they thinking? They obviously weren't thinking scale, right? So how about average? If you do pairwise average, you introduce division, right? That's not good. Not composable. But if you, so there's a couple ways to do this where you can actually maintain, right, like the local, so if you're going to add 3, right, like maintain the count for each of those. And then you could just do one big add, so that's composable, and then like another big add on the bottom, and then just do one big divide at the very end. Or you can actually calculate those averages and then store the count, and then do it that way as well. So that turns what normally would not be like composable into something that is like composable. Okay, this is the good stuff. So we've got different types of similarity, right? This is kind of the basic, right, like Euclidean flat space. You've got linear measurement. So the problem here, though, is that you've got one side is a scale of 1 to 5, and then the other one is on a scale of 0 to 50. So while these actually are similar, if you just do Euclidean similarity, they like don't seem similar. So there's bias towards magnitude. So we can switch over to be cosine similarity, and then basically convert it into where you're calculating angles, right? So that does the adjustment for the magnitude bias. Basically, yeah, normalizes things to the unit vectors. There's some math for you there. There's like Jacquard similarity. So we're starting to get into set similarity now. So to calculate if two sets are similar, so this comes into play when you have like a big matrix of users and then all the movies that they've watched. What you're trying to do is figure out, which users are similar to each other based on their movie views. So yeah, simple Jacquard similarity, intersection of the set divided by the union. The problem here is there's a bias towards popularity. So at Netflix, we actually had this problem. It was called the Shawshank problem. And it was kind of based on, like whenever someone would join Netflix, where like you were forced to say what your favorite movie is and favorite TV show. And people always, it was like 95% Shawshank Redemption. People from across the world that, probably didn't even have access to it legally still claim this. So you can like adjust for this popularity bias by using this log likelihood similarity. So basically factoring that out, and then you can now see other patterns, right? Like other things that are sort of like higher value. Because think of someone that's being presented Shawshank all the time. Yeah, that's not like very effective, right? But if you're shown Saw 3, that's super valuable. All right, so this is word similarity. This is getting in some of the like text-based NLP type stuff. Yeah, we have some code there, basically trying to figure out how many differences are there between the words. A very common interview question. So now we have document similarity, TF-IDF. This is very common. Right, like you guys are probably pretty familiar with all these so far, right? This is all basic stuff. Okay. Yeah, how about word2vec? Yes, anyone got word2vec to use? Yeah, have you used it? Yeah, how about TensorFlow? Have you used it with TensorFlow? I'm going to try to show that demo as well. But so the idea with word2vec is that you're essentially projecting, so there's this vector space, right? And you sort of comb along the text and figure out which words sort of lead to the context around that word. And so the sort of end result here is that you can actually get words that are similar to each other And then if you project in one direction, you'll get words that are also similar to each other, right? So yeah, pretty cool stuff. What's cool about WordDevec too, I didn't realize this at first. I was still doing TF-IDF with WordDevec, but like you don't have to do any of that stuff, right? Like WordDevec basically does all the feature engineering for you. So it'll like get rid of stop words and yeah, do all the stuff that you would normally do with text manually. So text rank, yeah, has anyone used this? It's basically this combination of like TF-IDF building a similarity graph, right, like between all of these sentences, and then piping that into PageRank and figuring out what are the most influential right, like sentences of a particular document, right? So this is good from if you're trying to like summarize a huge corpus or just trying to get like an abstract. Yeah, this was used actually. Yeah, my friend Paco Nathan actually built this with, I think it was Rolling Stone, you know, back like 10 years ago or whatever, to sort of go through all of their old right, like reviews and things like that and pull up the summaries there. So here's an example of a similarity graph. So each vertex would be like a movie, if that's like Sleepless in Seattle or whatever. So it's like related to other movies, or it's like it is featured in a particular, or it's in some sort of location, yeah, shot in location. And then, yes, each of the edges, so that actually, yeah, so those are, right, like the weights or the strength of that relationship, right? Yeah, things like plot summaries, stuff like that. So this is right out of Netflix. This is actually fairly recent, probably I think last summer. It's right, like the ability to sort of start at a node and then find, you know, all of the nodes that, yeah, so basically take each node, which is a movie, for example, and pre-process. So go through the entire graph, figure out the probability for each of the other nodes, right, like vertices, that probability of if you started there, you would end up at that node. So this is pretty powerful because now you can actually sort of right, like diffuse out. You would start with one node and then go through and sort of pick up the most probable right, like other nodes based on this graph. So that, yeah, so that would lead to things like right, like zombie movies. Yeah, it's got okay. And then this is kind of fun too. I actually built this. I have a demo of this. If you're sitting down, you know, it's Friday night, it's like you and your honey or whatever, like trying to figure out what to watch, you would each pick a movie, and then based on similarity, similar plot, similar actors, similar, right, like location, cast, all that stuff, find a movie that's in between. And I think actually Comcast Labs actually, I think had this. I found an app where you can actually go into like party mode and have 4 people pick a movie, and then you all, I don't know if you could actually watch it together, but yeah, they actually implemented something like this. So this is item-to-item similarity graph plus Dijkstra's shortest path, right? Trying to figure out. So how do you calculate similarity? If you want the exact similarity, what you'd have to do is basically do an all pairs similarity. So start with the first row, for example, and then compare it to all the other rows. Go to the second one, compare it to all the other rows. This is huge. The physical implementation has the word Cartesian in it. Bad stuff. What you want to do then is just switch to these approximations where you're either sampling, so you're like reducing the size of the amount of data that's being compared, or do bucketing, where you're actually, so you can bucket by genre, bucket by geolocation. Yeah, those are kind of the obvious ones. But there's ways to actually like statistically go through and figure out which movies are with high probability similar to each other, or which users, like whatever you're trying to find similarity with. Some basic recommendation terms. The big one here is probably explicit versus the implicit feedback, right? Like, have you guys heard this term? So the explicit, that's when you're actually rating something. So that was the old way that Netflix would actually figure out your preferences, right? The problem there is that, yeah, so not a lot of people did that. They wouldn't actually return the DVD and then go online and then rate it. So when they switched over to streaming, they were able to actually capture more. So they were able to capture like play events, and if you would watch the entire series all in one weekend. Because the problem is once that DVD ships, they don't know exactly your pattern. And so now you can actually get finer grained. So they can start to cluster people together that spend the whole weekend like watching some new series. Yes, I actually didn't watch that much like TV when I worked there, which is kind of funny. And then, so cluster those people together based on like not what they're watching specifically, but their actual behavior. Yeah, we'll talk about cold start in a sec. So features, different type of features. This is what you're actually piping into these machine learning algorithms. The key ones here are probably categorical. So if you have like various categories so picture NFL teams, for example. If you first assign 1 to Bears, just switch over here, 2 to 49ers, 3 to Steelers, if you pipe that into these machine learning algorithms, they're going to start to make like assumptions that Steelers is 3 times the Bears, things like that. So there's this technique called the one hot, where you can actually go through and like normalize it. So if there's 3 teams, there would be three like elements in that vector, and then just one of them would be 1. That way you're sort of normalizing in between 0 and 1. But there are things that where order does matter, like size, small, medium, large, that kind of stuff. So there's a couple types of recommendations. Obviously non-personalized. The cold start problem is like pretty common, right? Like you don't know anything about the person. Things you can do are just go back and look at the most watched movies, the highest or like rated movies, that kind of stuff. Use PageRank for like a dating site. If everyone's rating each other, you can figure out who are the most desirable, based on in likes and out likes, that kind of thing. And then certain people will rise up to the top. Something that actually changed Netflix quite a bit, this was actually like one of my last projects there, was we would integrate with Facebook. So so there were 2 things. When you first logged in or first created your account with Netflix, if you opted in, it would start to recommend what your friends have seen. And so you would see their face and be like, oh yeah, that guy has a very similar sense of humor. I'll go like watch that movie. But the other side of it was that we would actually post to your Facebook timeline. After about 5 minutes, we would post, and then other people can comment, and then there's a link to go click, and they could start watching it or start to comment on the movie, that kind of thing. Oops. Okay, so here's a form of personalized recommendations. Oh, actually, sorry. This is more of okay, so we'll just talk about clustering here. So there's user-to-user clustering. I mentioned like movies watched, right? Like similar movies watched, similar movies rated. Their viewing pattern. And then there's item-to-item clustering. So if you take someone's profile from a dating site, for example, and if you run TF-IDF or pull out some of the like higher value words, you can then compare it to other people's profiles. That second example in the middle, that's also from a dating site. So you can tell I spend a lot of time on these dating sites. You can pull out, so now this is categorical. This is, I've chosen Catholic, I've chosen I like dinner, I like live music, things like that. So now you can start to find similarities based on these things. And then this third one here is pretty interesting. This is actually from a blog post. If you Google Tinderbox, right, this guy actually like reverse engineered Tinder's API. And did all kinds of stuff. But one of them was keep track of who I'm actually liking, and then now go through, swipe, and so I think it was after about 160, you sort of build this eigenface, like an average face of the person. And I think there's 27 points, right, like unique points on a person's face. And so now, basically auto swipe for me. Right, because he's such a busy guy. He's on so many dates that he can't even swipe on his own. So basically, as these faces would come in, and They all don't have to be perfectly this way, right? Like you use convolutional techniques where sort of going around and finding, and then it'll figure out, right, like where these things land and yeah, if they are similar. Oh yeah, I don't think I actually have it in here, but like one of the other things he did was this conversation bot where he would essentially fire off just kind of a generic, softball, hey, yeah, how's your weekend, or blah, 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 whatever. And then based on their response, would run sentiment analysis and then figure out. And so there was this hierarchy thing. And then, yeah, so each day he would get a report that showed which girls, yeah, he was interested in girls, were sort of, right, like showing interest. So it would filter down the people, yeah, that he was interested in. Yeah, he's a pretty good looking guy too, so I can understand why he has problems like this. And then, of course, there's the classic user to item. Yeah, there was the Netflix challenge, right? Like, do you guys know about that from, it was probably 10 years, 15 years ago. So, yeah, essentially using collaborative filtering, take that snapshot, that matrix on the left, right? Like, take a snapshot of it. There's, yeah, I'm just doing likes here, so zeros and ones. Factor it out, right? Like algebraic factor. But yeah, this is matrix factorization. And then, yeah, so once you find two of those smaller like matrices that when multiplied together create that big matrix, right? Like now you can start to fill in like some of the empty things. So when user 3 walks in, or yeah, walks in, or like logs in, you just basically sort or keep the top 5 or whatever, and then show them top 5 right when they log in. And this is just simple dot products, right? This is like super easy math. All right, there's item-to-item collaborative filtering. So this is 2003. There's a pretty famous paper about this. I'm not going to go into too much detail, but the challenge was that they couldn't scale. So they were trying this, but so you've got users on the left, and you have books and right, like movies and stuff on the top going to the right. When M, which would be users, started to grow past a certain point, and it's trying to, like factor out these matrices, things would just break down. So they went the other way. They actually went with a smaller dimension. So say they had 30,000 movies or 30,000 books, and then just basically figured out ways to recommend off that. So this is item-to-item collaborative filtering, not just simple item-to-item similarity, which would be like based on the metadata like tags and things like that on these books. So essentially they would use the customers that have purchased these books and then project that out and then into this vector space. So every customer is a different dimension. That item is now going along that, right, like those dimensions, and then figure out who's in that same, or right, like which other items have been projected around that same space in this super multi-dimensional like vector space. And so then, yeah, so as you were going along, right, like putting things into your shopping cart, it would start to then recommend things that were in that same space. All right, so when do you use approximations? Yeah, this was one of the other topics yeah, that I wanted to focus on today. So if you have memory constraints, time constraints, so the huge example, I like experienced this a few years ago, right, like Netflix would do releases every couple weeks, right? And each time there was a release, right, like errors would happen. The most classic one that probably affected all you guys is you would be forced to put in your like username and password again. And that was like the worst. Like we would lose customers over this. People would just never log in again. So that had a really particular error code that we knew about. So we were always keeping a like track of that specific error code. But for me to run and to find those counts to see if they were elevated from right, like the previous hour, previous 2 hours, was the super slow Hive query that took 45 minutes, right? So Hive generates MapReduce. Right, like MapReduce needs all these servers. It's trying to get right, like the exact count. And there were thousands of these streaming servers that were throwing this error that we were scraping logs off of, right? So the entire pipeline was probably, right, like just to get the data was about an hour. and then to run the actual like Hive query was 45 minutes. So by the time I figured out that there was an error, right, like besides my sister calling and saying, hey, there's an error, then yeah, I was already 2 hours out of date. So using some of these probabilistic methods, you can actually get a sort of just like a relative count, right, like a rough count, because I didn't need to know the exact number. I'm not really giving this to the SEC or anything. This is just like from my own knowledge. Is there something that's like higher than before? So if you're using any kind of machine learning or like graph algorithms, these are really probabilistic by nature. So they're not giving you the exact values, right? So this is okay to approximate or to feed in approximate data, right? So yeah, there's some examples. And then streaming is interesting because there really aren't very many, there are, but it's not very common to spend a lot of time on, like specifically these types of like media sites. Back in Chicago, I spent a lot of time making sure every single like transaction got through, there was no duplicate data, that kind of thing. Yeah, that's why I moved from Chicago, because that's all I spent my time on. But now I can actually, this whole streaming pipeline is a little bit sloppy to begin with, right? Yeah, we're not necessarily losing things. Yeah, we've solved that problem pretty well with things like write-ahead logs and that kind of stuff. So we're not losing data, but there could be duplicate data. So yeah, not the end of the world. So yeah, here's my recommendation. Approximate as much as you can, and then ask for forgiveness when the business guys come to you. So when not to approximate. If you've ever heard this, Sarbanes-Oxley at the office. Yeah, these guys, they're why I moved from Chicago. Okay, so let's talk about some of these algorithms. These are the common characteristics of these approximate and like probabilistic algorithms here is they're typically fixed memory. So take the use case where you're trying to count errors, right? If you're going to count, right, like each and every error that comes through your pipeline, you basically and if you're trying to store that in memory, like this system that we were building at Netflix that was similar to Kafka, similar to Spark streaming, you basically have to have a huge hash map or a hash set, right? And it has to add one each time, and it's basically like you're going to blow through, right? Like any sort of like if you keep scaling it out, that's one thing. You just keep adding more and more Redis servers or right, like whatever's in between, storing this stuff. But it's basically just going to blow through any like kind of memory constraints that you have. So right, these probabilistic data structures actually are fixed, so maybe 12K, something like that, and they can store a whole ton of counts. So you can just keep adding more and more. I think it's like 10 to the 9th or something like that, right? And they're tunable, so you can actually, if you're okay with more error, but you want more counts, yeah, right, then that's okay. You can tune these things. So typically you're hashing as well, and like you're applying multiple hashes, or you're taking one hash function and then breaking the right, like data up into multiple subsets and then running that same hash and then averaging. Yeah, so so we'll talk about hash quite a bit. Oh, and then yeah, of course the size of the right, like the hash range. So probably the simplest one to reason through is Bloom filter, where you've got just a big a big bit set. And there's a piece of data coming in, there's some key, like the error code, for example. You're going to hash that. It's going to hash like multiple times and then end up flipping bits in like different parts of this gigantic hash set, or like bit set. So these bit sets are small, but the problem is that these hashes could like overlap with each other, right? Like the bits that it's flipping could be flipped by two different keys, which is why you do it multiple times. But if you have a larger range, it's less likely that like you'll have these collisions, right? So Bloom filters, this is sort of the big thing about Bloom filters is that you can basically ask it. So this is for set membership, right? So now you can ask, does this set that I've been maintaining in the Bloom filter have this error code? So it will always tell you the true negative, but it could give you a false positive. So basically, you're expecting it. It could say that it's there, but it might. Let's see. I think it like maybe contain, but it will definitely not contain. Right. So these are the return values, true or false. Yeah. So again, so on the write path, when we're setting the key, it's going to hash into multiple areas, flip those bits. On the get side, it's going to run those same hashes, find which bits I should be checking, and then if they're all flipped yes, then that's a maybe. But if there's one of them that's flipped no, then that's a definite no, because it means it's never flipped that bit by like any of the keys that have come in. Okay, CountMin sketch. Similar to Bloom filter a bit. The use case here is top K counting, frequency counting. So we're trying to approximate. So now this is perfect if I'm trying to approximate, right, like the number of like errors, for example, or like heavy hitters. So now, yeah, this is a Twitter term, right? Like a lot of these algorithms that I'm going to demo are from Twitter's Algebird project, which is a bunch of these algebraic monoids that are like composable, things like that. They have all the good parallel properties that we were talking about. So heavy hitters, I was in, I think it was Zurich, Switzerland, and I ended up meeting this guy. Yeah, does anyone know this guy? Yeah, like Johnny Holiday. He's like, yeah, I thought he was like a crack addict that was sitting next to me at the bar, but he's like the Elvis of France, and yeah, he was sitting next to me, and he didn't like me at all. I was trying to make jokes. Yeah, Martin Nadersky's a heavy hitter. Yes, we just had him on Thursday in town. He was really, I thought he was going to punch me in the face for like demoing this, but yeah, he was actually laughing. Yeah, he says that like he should grow a beard because in history, all of the great computer scientists who have created languages all have beards. And he like rattled off a bunch, and I was like, yeah, I trust you, man. And then Trump, yeah, he's a heavy hitter. Yeah, I was in Europe when all this was going on. I was like, is this actually happening? But okay, so CountMin sketch. This one's actually relatively intuitive. My depiction here is going to be a little crazy, but picture, so each movie that gets watched, we're going to send that into this pipeline. So we get Top Gun twice. So the first one we get, we hash it. Yes, actually, I added a tiny bit of complexity here that sort of works against me when I present it here. But if you hash it once and then add it, so each row is a hash function, and you take the binary output of that hash, and that translates into the columns. So the zeros and ones. So you would flip 0, 0, 1, 0, and then the second one 0, 1, 0, 0. All right. So just bear with me here. You do that twice just because I put it in there. And now there's a few good men comes in. This guy hashes differently. It's the same hash functions, right? Like that's sort of the premise here. So now so there is overlap here with Top Gun. So there's an extra one going into that slot, and then we put 1, 1 there for those last two hashes. And now I picked all Tom Cruise movies for some reason. Yeah, has anyone seen Taps? It was his very, very first movie, I think, like before Risky Business and all that. So Taps comes in, hashes this way. So now there's overlap with A Few Good Men, just by the way that the hash functions work. So now on the get path, so that was the write path. So now if I want to get the count for Top Gun, I'm going to run those same 3 hashes, go to those slots, right, those coordinates, and take the minimum. And the reason that we take the minimum is the same reason that we don't want to, the Bloom filter side of things, we always want to take the minimum, right, 0. If we find a 0, then, because we don't want to overestimate. So here we're taking the minimum, it's approximate. In this case, it happens to be correct. So yeah, this will never underestimate, but could potentially overestimate based on those collisions. All right, does that make sense? Yes? No? Hyperloglog. Yeah, Sonia and I spent hours. Well, yeah, she spent hours explaining to me. Okay, so this is an approximate count distinct. So that's what's different here, is that Hyperloglog is about distinct values, not just like top K, that kind of thing. So there's a slight twist with Hyperloglog in that the whole hash function here has to generate uniform distribution. That's like the whole basis of this technique. But there's not that many. So it's a special hash function. So now this is the case where we actually break the data into subsets and then apply that special hash function on those subsets. And then we're going to average them out using, yeah, Sonia, what is it? The G, no, yeah, the harmonic. Right. Okay, and then there's not many of these. We can estimate the error. So again, if we assign 14 bits for this huge bit set that we're hashing into, then we can actually calculate that creates 16,384 of these slots. There's this formula 1.04 divided by square root of that number of slots. That ends up being 0.81. So if I give 14 bits, then yeah, that's my error. And the more bits that you give, right, the lower it goes, but the less counts you can maintain. So here's those slots I was talking about. So there's movies coming in. We're trying to maintain distinct number of views. So each time it comes in, we're going to, and so here's that like uniform distribution. So, oh yeah, right. So like for this use case, we're trying to figure out distinct number of users who have watched it. So every user that comes in, right, so it's going to come in with a user, comma, movie pair. And I'm going to find the Hyperloglog structure in memory that I'm using, and I'm going to hash that user ID, and that's going to end up really going into this uniform distribution. So what's cool about the uniform distribution is that you can actually, when you go to actually do the count, you can just take a small amount, and right, like because you know that there's two slots in between, yeah, so now you can estimate over the whole thing. So this is hour one, this is like early in the day, whatever. There's only 16 slots. Yeah, now we have hour two. We've given it, for like larger amount. But to actually do on the get path, what you're doing is just looking at a small subset. And then you can estimate it out based on the number of slots that you have. And you can compose these, so you can actually squish them down, right? You can just do plus plus, whatever, add it. And you'll lose a little bit of precision, but you can get an approximate for those 2 hours. Okay, so here's another one, locality sensitive hashing. So again, this is trying to figure out set similarity. So we switched from counts now to similarity. Yeah, back to similarity. This is an approximate set similarity. What? Are you kidding me? This is like, yeah, everything that could go wrong has gone wrong today. From my doctor dying to my battery to everything. Yeah, locality sensitive hashing. So we've been given this huge thing of this huge vector. There's some attributes to it that we're trying to compare to figure out which ones are similar. So picture these are users, and each of those vectors has, right, like the movies that they've watched. So if you do it the naive way, you have to take the first one, compare it to all the other ones. Take the second one, compare it, and then figure out which ones are the most similar. But so, right, this was the Amazon problem. Once M gets so big that you can't, that just doesn't scale, what you can do is do one pass through all of the data. So that's OM, I guess here, because it's M. So it's just one linear pass through. And then, yeah, so you can apply like hash functions to figure out which buckets. So if you say that you want 50 buckets, for example, it's going to go through and could assign that same, that same item to like multiple buckets. But the key is that you're taking this huge list of M and now breaking it down into just 50 buckets. And so now you can do the exact compare within those 50 buckets, right? In parallel. So each bucket gets compared, just the contents of that. So it's still Cartesian, but it's within a bucket. And it's much less than if you're doing Cartesian on the whole thing. That's the intuition there. So pre-process, get down to B instead of M, and then within each B, then you do the full like comparison. And of course, you can do that in parallel too. So from a wall clock time, right, like you can do all 50 at the same time. So this is kind of interesting. This actually made it into the Spark core. This was a joint collaboration between a Stanford professor who also works at Databricks and Twitter. So yeah, Twitter had this problem. They were trying to figure out ad similarity, or yeah, trying to figure out which ads to show to like different people, finding people that were similar, finding ads that were similar. But they had that exact problem where, yeah, so they were using cosine similarity, but they just couldn't do that huge Cartesian. So they used, yeah, so they actually implemented, it's this sort of probabilistic way of going through and taking out these items that there's no chance that like they could be similar to other items, right? So it's sort of a, like this is a sampling technique. So you make one pass through, pull things out, and then just compare this much smaller set. So this affects shuffle, right? Because like whenever you're trying to like compare things, you have to get them onto the same machine. So that's where the HDFS, or yeah, that's the bytes read, bytes, yeah, the shuffle bytes, everything. So that was the day that they put it in, and it went down by 40%. So they're able to show ads quicker. They're able to show them in a smaller amount of time, more real time. So here's some of the libraries. We got Twitter Algebra. Yeah, so Redis actually has Hyperloglog now. As of, I think, about 2 years ago. There's a really good paper about Hyperloglog that is associated with right, this Redis release. It was a blog post when they first started implementing it. So Algebra, yeah, the reason it's called Alga is because it's rooted in algebraic. Parallel, associative, composable, all the good things that we've talked about. Supports all the basic ones, and then of course Bloom filter, Hyperloglog, CountMin sketch. It's got a bunch of other ones like all these special decay functions, things like that that are like Approximate. And of course it's all based on monoids. And then yeah, this is my favorite. If you guys can see it, there's a comment in the code that's like, don't worry about the name, just stick with me here. Okay, so Redis, this is out of the box. This is tunable though, but 12K per item count. So that would have been Top Gun, and then those users coming in. Yeah, I've allocated 12K. It's fixed. I can maintain 2 to the 64th max number of those users coming in. And it's 0.81% error because we're giving it 14 bits. But that's tunable. Here's the API, PF add. The reason it's PF is the guy that created like Hyperloglog. His name is yeah, those are his initials. I can't say his name, but it's and then yeah, so PF add, that's where you're actually adding those users into the Top Gun HLL data structure, and then when you go to get it, you do PF count, and that's going to return distinct users. It's just going to inspect that small part of the huge bit set, and then return like an approximate. And of course, you can union these. Yes, I showed that they're composable. So here's some approximations in Spark. You'll see on the base RDD class, there's these methods called like count something approx. Yes, obviously these are approximations. They use these techniques beneath the covers. If you notice, yeah, not many people know about this. There's this partial result concept. Like there's actually a whole package within the Spark code base. It's org.apache.spark.partial or sparksql.partial, and it's ways to fire off a job and then like just cut it short and then yeah, collect everything back. So that this stemmed from that project BlinkDB. Yeah, if you guys have heard of BlinkDB, it was a pretty active project back in the day, but some of those concepts have now rolled in because yeah, they actually hired the guy that created that. There's a Hyperloglog Plus that's within Spark SQL. There's a first class thing on, I think this is on data frame, the approx count distinct. And of course, Spark ML has a lot of these. It's got the dim sum. There's a sampling, stratified sampling where you're sampling from, by key. So if you have skewed distributions for each key, like you don't want to oversample from one of those keys. Oh yeah, and then Spark Streaming, Spark 1.6 just released a way to do A/B testing. Yeah, I don't know much about it, but there's a way, as data's coming in, you can basically pipe it to one area or pipe it to another, and then compare the results. All right, so I can probably show these live because I think this part will work, but this is the results here. So this is Hyperloglog. So yeah, again, count distinct. I have a set of 100,000. Yeah, there's like this really cool like utility function that I found. This guy. So yeah, he's actually the Spark Meetup organizer out in like Bangalore. I think he's like number 2 or something behind Databricks. He actually went into the Spark code base and pulled out the code that is used to like estimate when they should spill the disk. So taking a look at an object, like going down the hierarchy. That's actually surprisingly hard on like the JVM without like turning on a lot of these sort of external flags that you would never want to run in production. So what it was used for within Spark, and it's not used much anymore, was as you were doing aggregations, right? As data was coming from mappers to reducers, or trying to aggregate things, trying to reduce things. At some point, they had to figure out when they should spill the disk, basically, right, to avoid the out of memory. So he pulled this out into this utility function. I'm using it because it's actually pretty accurate. If you run it on string, for example, just like a 3-character string, it's actually 48 bytes within Java because of all the overhead of the Java object structure, all that. So now there's Project Tungsten, which actually stores everything in big ass byte arrays. So they can just do a count on the array, and they can get an exact count of how much memory something is taking up. Putting in those 100,000 and then doing the size estimate. So this is in memory. This is in the JVM memory. Now I create Hyperloglog, give it the 14 bits. I give it the set, and I do size on that, and it's it's like 12K or whatever. Yeah, I think it was supposed to be 12K. Much, much smaller than if you put those 100,000 into an actual set. Right, so those would be keys. I'm maintaining 100,000 users coming in, and I'm keeping counts of those. Same thing, CountMin sketch. So now this is top K. That's the same number as before. Give it some parameters there. Same exact set, 300 K versus 7 megs. So here's locality sensitive hashing. This is that Cartesian. So this is that bucketing thing I was talking about, where we're going to pre-process. So if you just do Cartesian, just the naive brute force way, let's see, it's going to generate, what is that, 450 million items that it has to compare, because I think I'm passing in 30,000. So yeah, 30,000 times 30,000 has to compare all those. So that's a lot. That took about 90 minutes. And then we switched over to locality sensitive hashing. I actually screwed up the way I was doing it, so it's not these numbers, 150, but it's, I think it was about 3 orders of magnitude less. Okay, any questions, by the way? I tend to talk a lot. Do we have time for the Netflix stuff? Okay, we're on slide 65. Wow. So the whole thing here, there was a challenge. It was started in 2006. It was presented out to the community. yeah, so Netflix took a bunch of sample data from their live data, pulled it out. They held out 20% or some percent to run to test against, like whatever model that you give them. That was actual data. They gave you the other 80% for like training purposes. This is also the same data set that there was a class action suit a couple years later, where I think some statisticians from, can't remember the school, CMU or something like that, figured out that from that data set, so that data set by itself didn't have any like unique identifying information. It was all like PII safe. But when combined with IMDb, you could actually find like a high correlation that it was that particular person based on the pattern. So yeah, it was pretty complex to spend the time proving that. And like they waited until the prize was awarded. And, yeah, so then there was like a monetary thing involved and all that, which is pretty interesting. Yeah, and so the final winning algorithm, this ended up being this huge ensemble of 500 some models combined together with gradient boosted trees. It just wasn't practical. I mean, it wasn't computationally practical. Again, this is 2009. But yeah, Netflix did learn from this. They pulled out some of the good pieces. Some of the like higher level concepts here, this is actually how they, so like teams would like get together and they would start to, they just couldn't make any more progress, so they'd partner up. So yeah, this kind of, there were, I think, 3 teams like ended up combining and then winning. But what they like neglected to do from the beginning, so there's timestamps. So it was like user, movie, and then like rating, and then timestamp. And they sort of like ignored that at first. They didn't really think that time would matter. But there's this huge like human element where the people that rate a lot like tend to get more and more critical as time goes on. So that's called the Alice effect. And then there's this thing about the inception effect, where the longer a movie has been out there, and like so they defined that by the first time a rating was given, that would also like affect. So certain movies would actually get like rated higher on average because they heard good things. That's why they're watching it. They knew it was going to be a good movie. Yeah, then there's the like combination of those two. And then I was just reading the other day, there was an article from like one of the execs of Netflix that came out about if they're going to ditch the actual rating system because there's really no value to it, or there isn't much value to it anymore with all of the implicit feedback. I forgot, I'm not sure if I called that out specifically, but so rating is the explicit, and then views and things like that, you're actually viewing like pattern, that's all the implicit data. So the problem with people rating too is that you could rate a movie that was a shitty movie, but like you actually like really enjoyed it. Trying to think of an example, maybe like Waterboy or something like that. Like it was an absolutely like horrible movie, I thought, but it people still keep watching it. And so if you give a bad rating, that's confusing the quality of the movie, or it's conflating quality of the movie with your actual, like the enjoyment that you got out of the movie. So they were thinking of doing like a thumbs up, thumbs down, or like a percentage, like the Rotten Tomatoes kind of thing. So let's see. Oh yeah, and then number of people who have rated. They started to take a look at that. So the whole thing here was that they could now start to adjust, right? So based on time, you could sort of, tweak like some of those recommendations based on how long someone or some movie has been rated. Quick blurb on the pretty recent Netflix architecture. Spark is in here. It's not on there specifically, but there's this sort of offline batch. So that was kind of the beginning. That's how Netflix operated. Basically pipe all this data in, all the viewing data, churn, it would take 48 hours sometimes, whatever. And then create models from that. And then there's a sort of near line, near real time, where it was spending quite a bit of time. They built this whole EV cache layer, which was like Netflix specific layer. I think it's open source, but like nobody uses it. On top of Memcache. And let's see, yeah, they use MySQL. So basically, sort of adapting, right, like throughout the day, but not really like a true online type thing. So now they've gotten more and more online. Yeah, pretty natural stuff. So we worked with them about a year ago to get Spark streaming going, to get Kafka going, things like that. I think they were looking at Samza for a little bit, which is a natural, it's like out of LinkedIn as well, so it worked well with like Kafka, but I think they ended up going Spark streaming just because they have Spark everywhere else now. So yeah, this is like throughout the day, this is actually making tweaks. So this is where you get things like personal trending. So there's sort of what's trending overall. Yeah, that's pretty easy to calculate. But then there's what are the things that I like that are trending, right? Or people like me that are, yeah, things like that. So they've spent a lot of time with this sort of personalized trend. Yeah, there's a really good blog post came out just a few months ago about this. So this is where you see some of the like algorithms coming into play. One thing that they do that's pretty interesting is they calculate the video factor. So this would be the item factors. So picture that like matrix factorization. They would calculate one side of that and then throw away the other. And then in this like near real time, right, like throughout the day, right, yes, every 4 hours, something like that, they would then calculate the user like matrix there, and then they would run dot products, make recommendations off that. So yeah, that was kind of interesting. Here's a list too of some of the, yeah, these are fairly current. So they use like quite a bit. Actually, I was just talking to one of my buddies. Yeah, they use like the whole logistic regression. That's basically the heart of all. I mean, that's the first bullet point on there. But yeah, that's like it's pretty. It scales really well. Things like that. So that's their bread and butter algorithm. Yeah, SVDs. Yeah, a lot of matrix factorization. Starting to do some of these neural networks. Yeah, they use LDA to sort of cluster movies together. So they ran LDA and on all of the movie metadata and actually started to find clusters that they didn't expect, right? Because if you're doing any kind of clustering, just sort of unsupervised, you sort of give it the number of buckets. Like you say, I think there's probably like, if there's 50 genres, there's probably 50 buckets. They started to expand that, right? Yeah, that number a little bit. And found things like Bollywood movies and things that didn't fit into the classic tags that they had been using. And then, yeah, I found this pretty interesting because every site that I've ever worked on, like the last 5 years or 10 years, if there were no results, yeah, you got no results, right? And like we would track that, like we knew, yeah. So we had counts and would get reports throughout the day of people searching for something, and then we'd quickly go and add content or try to satisfy the search. But yeah, there's no reason why you basically can't run a recommendation, off of these search results. So first go to the search engine, nothing comes back. Now start to figure out what else we can show. So there's never a zero result response. And that's it.
Thank our speaker.
Thanks for coming.
I know some people have to go, so it's a good time to stand up. But if you have any questions, maybe we'll take one or two.
Yeah, for the just curious for the Tinderbox developer. What was that gentleman's name?
Yeah, he's out of Vancouver. I'm going up there and I'm trying to get with him. Let me find it. He's got this blog post, Crock-Pot Veggies. Veggies, it's kind of a goofy name, but yeah, he got so much interest in it that he finally said, like, I can't keep up with the support on this thing. But yeah, this is it. But the NLP stuff I thought was actually really interesting. So here's the eigenfaces. Yeah, he's got the code in here. This isn't Spark code. This is just, but yeah, this is the conversation bot. So it kind of goes down the chain, and then it surfaces people that have made it past a couple just like generic responses. And then, yeah, he built this dashboard. Yeah, he said he saved so much time with this automation that he decided to spend some time building a UI so it would actually like show him all these pie charts and stuff. And here's the GitHub. Yeah, there's GitHub, but there's a huge disclaimer like, I have nothing to do with this anymore. Yeah, he's using Core NLP. Yep.
Thanks, that was great. You had some demos that we didn't have time for, which is great, but you mentioned they're downloadable. So could you just describe what's in there?
Yes, so here they are here. Here's pretty simple, like Hyperloglog ones. This is where I got the screenshots from, showing the different sizes. Here's simple clustering, similarity. Here's the locality sensitive hashing. Yes, you guys can actually go to this right now. I mean, it's not stable, like I take it down when I'm doing upgrades, things like that. I've been trying to put images in there that sort of give you context. The different data sets I'm using are the movie lens data set. There's a like dating data set that I grabbed. Some guy did his PhD and out in I think Prague or somewhere, and convinced this dating site to give him like a bunch of anonymous data. It's not really that interesting because you don't really know what these people look like or anything, right? So, but yeah, this is movie lens. We're doing clustering here on these genres. Let's see. Classic PageRank, nothing too exciting there. This is using GraphX for shortest path. This is that Similarity Pathway one. Yeah, this one's really cool, and this should work, I hope. But you essentially, at the very end, give it a movie to start with. So I want to watch Toy Story. My non-existent girlfriend wants to watch Sudden Death. How do we resolve this, right? So I've already pre-processed like this entire graph, and I'm going to do some Scala goofiness here with underscores. And my results are, this isn't formatted very well, but I start with 1, and then 10 is in between, and then destination is 9. Yeah, so basically it ends up being this right here. Toy Story, GoldenEye is the common factor. This is just a very small data set. I only did, I think, 10 items or something for here, but it matched it on these tags. So they're the most similar based on tags, right? For the genres. That one's pretty cool. Then real quick, just a couple others. That would be from the live demo. I was gonna have you guys select the tools that you use in production, right? If you use Presto, if you use Spark. And then I was gonna make recommendations based on this group. It was totally personalized to this group. Which other projects you should be looking at based on what other people are using in production. And then this is my favorite. I'm a big country music fan and sort of had this intuition, this is strange, I know that country music is depressing, but I had to prove it because, I need data to actually prove it here. So if you do just a simple, these are the top 10 words or whatever, love and gone and old. And now you do, n-grams here. So this is all right now Spark stuff. I just last night got, so these are n-grams, Vroom Vroom is in there, double XL, coming home. But there's a really cool one. I did LDA, actually didn't produce anything interesting. So this is like Word2Vec. We can do similarities. The Spark Word2Vec is actually pretty weak right now in terms of compared to like Gensim or like TensorFlow. I'm all TensorFlow now, by the way. So truck, produces chair and give my truck back. Love, hearts, like NASCAR. That's my favorite. God, shame and proud, all that. And then one last one here. So here's the sentiment analysis. So obviously the Spark stuff doesn't have sentiment analysis in there, but oh no. It ended up being, out of 100 songs when it analyzed all the lyrics, I think there were 92 that were negative and 8 that were positive. So it basically, looks at each word at each sentence at the sentence level and then rolls it up into one big one. But these are all out there. Some SQL examples. And then I've got a bunch of to-dos, things that are going to start filling in as I get more time. Oh yeah, here it is here. I'll just show you the end. So this is actually, I'm using Spark has a wrapper, Spark-Core NLP. That's not part of Spark itself, but it's a Spark package. Let me show you guys this just real quick so everyone knows about this. This is anything that doesn't go into core. Yeah, so Databricks, the Spark community has kind of put a fence around core Spark because what they realized is as they were accepting more and more things and things that were like Amazon specific, and yes, I wrote the Kinesis like streaming adapter, but these people tend to just disappear, right? Yeah, I didn't disappear, but yeah, these people disappear and then they have the burden to maintain it because now it's in core. It has to carry over from like release to release. So they've been putting up this fence, and if you search on Spark Core NLP, there's two that I want to show you. So Spark Core NLP, it's a wrapper, so now you can actually plug it into the new Spark or like pipeline API. So you can actually do some Spark stuff, then do some of this Core NLP stuff, take the output, go back into Spark land, all within pipelines, which come from, the concept comes from scikit-learn pipeline. And then there's one other that I've been working on, streaming matrix factorization. So this is actually, so really before I was talking about as data comes in, I store it in Cassandra, and then every hour I'm, like generating recommendations and then dumping them out into some database that then when the user logs in queries. This is actually on the fly. Yes, all these link to like GitHub projects. So, but yeah, Spark-packages, it like has its own Maven repo. The whole Docker image has all that set up for you, but you can just pick any of these. But yeah, so this is as data's coming in, it'll train on the fly, and then it'll predict on the fly as well with the most up to date. So it's sort of like what like Netflix is doing, where they're throwing away one of the like dimensions and then recreating things like that. And then oh yeah, so here's the sentiment. And then yeah, this will be it, David. I promise.
All right, no. And then if there's any other questions, just feel free to come up and chat with the speaker. Yeah. But let's thank him one more time.
Thanks for having me.
Great job.
Right on. Thanks, David. Yes, was that useful? Was this interesting? Yeah. Some? Okay. I'm waiting for that day where someone's like, fuck no, man, that was the worst. Get out of my building.
I'm sure they would have